To understand how digital systems work, we first have to understand how you can represent numbers in the Arduino processor, which fundamentally only knows zeros and ones. And that leads us to the idea of number systems and bases. And that's kind of the foundational math we need. You've seen this before, but to remind you. As a matter of fact, let's start with something you're really familiar with, which is how the base 10 system represents numbers, just to remind you of how the system works, and that hopefully will help you learn the other bases that we might need. So let's do a decimal number. And how about the number 347.2? And I'll write a little 10 down here to remind us that's in base 10. So what does that mean? How do we interpret that number? Well, what it means is 3 times 10 to the 2. And the 10 to the 2 is encoded in the fact that this is in this particular position after the decimal point. Plus 4 times 10 to the 1 plus 7 times 10 to the 0. 10 to the 0, of course, equals 1. And something you may not remember or think about much is plus 2 times 10 to the minus 1, which, of course, is 0.1. So that's what 3472 means. The little dot just tells us everything to the right is 0 and the positive exponents on our base 10, and everything to the right is negative n exponents on our base 10. And hopefully you sort of knew that, but that's just to remind you. Well, now let's use a different base, and all we're going to do is replace the base here. I'll write something different. And of course, the base of most interest to us, since we have these digital systems that can only represent zeros and ones, is binary. So if we have a big string of zeros and ones, how can we represent a number? Well, maybe let's just write a number in the binary system. Of course, we only get zeros and ones, because that's all binary has. So what would that mean? Well, that would mean 1 times 2 to the 2 plus 0 times 2 to the 1 plus 1 times 2 to the 0 plus 1 times 2 to the minus 1. Notice I've just followed the pattern. Before I had 10 to the 2, now I have 2 to the 2. I had 10 to the minus 1, now I have 2 to the minus 1. And the digits of the number 1, 0, 1, 1 are just written out and expanded. That's all this means. The positions here represent the powers of the number. And this is maybe worth going a little farther because you're used to this calculation. So let's go ahead and write that one down. 2 to the 2 is 4. So this is 1 times 4, so we get a 4 out of this. 2 to the 1 is 2, oh, but it's plus 0, so that's not so interesting. 2 to the 0, of course, is 1. 1 times 1 is 1, yeah. And 2 to the minus 1 is 1/2, so we'll write that as 0.5. So this equals 5.5. So cool, we can represent base 10. To be precise. So that translated from that binary to that decimal base number. The other system we may need occasionally, this is the most important one, is going the other way, using, instead of very, very few digits, much less than 10, a few digits more than 10. And this is called hexadecimal, which, if you know your Greek, means 16. So base 16 is nice, because it turns out that 4 digits of binary can represent 16 numbers, 0 to 15, and therefore you can take 4 binary digits and represent it as 1 digit of hexadecimal. So we often write binary numbers as hexadecimal numbers because it makes everything so much more compact, and the binary to hex mapping is nice and one-to-one. That may not yet make sense, but let's give you an example. Let's write a hex number. And that number might look like this. Now you're noticing I'm writing some letters, and that seems funny. But since it's hexadecimal, I need more characters than up here. We need more than 0 to 9. So what we do is we go 0 to 9, that's 10 total characters, then A, B, C, D, E, that's 5 more, F, 6 more, and that gives us 16 total characters, which is what we need for a base 16 system. So B is, A would be 11, B would be 12 in decimal. So let's write that out. B would be 11 in decimal. I did that wrong. 9, A, B. So 9 is the character 9, 10 is the character A, 11 is the character B. Sorry about that. And let's write that out. So this is, just following the pattern above, 3 times, base 16, 16 squared, because it's in this position. This is D, and D is 13 in base 10 times 16 to the 1, because this is the 1 power system, and then 2 times 16 to the 0, which of course, that's a 0, which of course is just 1, plus B, which we agreed was 11 after I screwed up, 11 times 16 to the minus 1. Same pattern as we had before. And now let's write this out in decimal. This is 3 times 256, which is what 16 squared is, plus 13 times 16, that one's easy, you just copy it, plus 2 times 1, plus 11 times 1/16, because that's what 16 to the minus 1 is. And if you add all that up on your handy-dandy calculator, you come out with 978.6875, which must be 11 times 1/16, base 10. So that's the relatively easy and mechanical process of translating any number in an unknown base into base 10. That's something you want to be able to do, just sort of understand the mechanics. The key idea is probably here in the middle, is that we can represent numbers as 0s and 1s, that if we think about this as a binary base 2 number of a certain number of digits, can represent decimal numbers. And that's what's really going on inside that Arduino processor.